Welcome back to Whispering Universes, where we chart the invisible pathways between stars and trace the hidden architecture that gives shape to everything we can see. Tonight we embark on perhaps the most ambitious journey we've ever undertaken together. A complete map of the universe, from the familiar ground beneath our feet to structures so vast they challenge the very meaning of the word large, and finally to the edge of everything we can observe and the tantalizing hints of what might lie beyond. There's a peculiar paradox in mapping the universe. Every map humans have ever made assumes a certain perspective, a place to stand outside the thing being mapped. A cartographer mapping a continent stands back, surveys from a hilltop, or flies above in an aircraft, sees the whole laid out below. But the universe has no outside. There's no hilltop in a higher dimension where we can stand and look down at the whole cosmic landscape. We're embedded within it, one small vantage point among countless others, trying to infer the shape of something we can never fully step back from. We're mapping a territory that includes the mapmakers themselves, charting an ocean while swimming in its currents. And yet we map. This impulse runs deep in human nature. This need to know not just where we are, but where we are in relation to everything else. Our ancestors mapped their valleys and rivers, their territories and trade routes. They mapped the stars into constellations, turning the chaos of night into navigable patterns. Each generation pushed the boundaries further, drawing coastlines and continents, hemispheres and globes. In the 20th century, we mapped our solar system with increasing precision. Now, in the opening decades of the 21st, we're creating three-dimensional maps of the universe itself, charting structures hundreds of millions of light years across, tracing the cosmic web that connects everything that exists. What do we mean when we talk about cosmic structure? We're referring to the way matter organizes itself across space, the patterns that emerge when gravity and expansion compete across billions of years. Structure appears at every scale we examine. Planets orbit stars, stars cluster into galaxies, galaxies gather into groups and clusters, clusters connect along vast filaments, forming a web-like pattern that stretches across the observable universe. Between these filaments lie voids, regions of profound emptiness. And underlying all of it, invisible but essential, dark matter provides the gravitational scaffolding that makes visible structure possible. Tonight, we'll journey through this hierarchy of structure, beginning in our cosmic backyard and moving outward in careful steps. We'll start with our solar system, that familiar collection of worlds bound to our sun. We'll venture to the boundary, where the sun's influence fades and interstellar space begins. We'll explore our stellar neighborhood, the local volume of space containing the nearest stars. Then we'll zoom out to see our galaxy, the Milky Way, in its full spiral glory. Further still, we'll examine the local group of galaxies, the small cosmic village we call home. We'll encounter the dark matter halos that surround and support all these visible structures. From there, our journey accelerates outward into the realm of the cosmic web. We'll explore galaxy clusters and superclusters, the largest gravitationally bound structures in the universe. We'll trace the great walls and filaments, vast assemblies of galaxies stretching across hundreds of millions of light years. We'll peer into the cosmic voids, those mysterious empty regions that occupy most of space. We'll discover Laniakea, the immense supercluster that contains our local group, a structure so large we didn't even realize we were inside it until recently. We'll examine the cosmic microwave background, the afterglow of the Big Bang itself, which shows us the seeds from which all structure grew. Finally, we'll venture to the edge of observation. We'll confront the cosmic horizon, the boundary beyond which light hasn't had time to reach us since the universe began. We'll consider dark energy, the mysterious force accelerating expansion and slowly isolating structures from one another. We'll entertain the possibility of a multiverse, realities beyond our own that might exist but can never be observed. And we'll reflect on what it means to be cosmic cartographers, intelligent beings who have emerged from the universe and turned awareness back upon itself, creating maps of the very structure that gave us birth. The universe we'll map tonight is not static, it's expanding, evolving, changing on timescales, both incredibly fast and impossibly slow. The map we create is a snapshot, a moment frozen from a continuous transformation that began 13.8 billion years ago and will continue for trillions of years to come. But even a snapshot of something this magnificent can take your breath away. So settle in, let your breathing slow and deepen. We're about to take the longest journey possible, traveling from our small blue world to the limits of everything we can know, and perhaps catching a glimpse of what lies beyond. Here on Whispering Universes, we believe the cosmos is most beautiful when seen in its entirety, when we step back as far as observation allows, and see the patterns that connect the smallest to the largest, the nearest to the most distant. The map awaits. Let's begin. We begin our cosmic map in the most familiar territory, the solar system, our immediate neighborhood in space. It's easy to forget how much this map has changed within living memory. When the first spacecraft began venturing beyond Earth in the 1960s and 1970s, our understanding of the solar system's structure was still remarkably incomplete. We knew the positions of the planets, certainly. We had catalogued thousands of asteroids, but the outer reaches remained mysterious, the boundaries undefined, the architecture imperfectly understood. Today, our map of the solar system reveals an elegant structure shaped entirely by one force, the Sun's gravity. At the center sits our star, containing 99.86% of all the mass in the system. Everything else, all the planets and moons and asteroids and comets, all the dust and ice and rock scattered across billions of kilometers, amounts to barely a rounding error in the gravitational accounting. The Sun's mass curves space-time around it, creating an invisible well into which everything else has fallen and now orbits. The architecture reveals itself as a series of concentric zones, each with distinct characteristics. Closest to the Sun, we find the inner rocky planets: Mercury, Venus, Earth, Mars. These worlds orbit in the region where temperatures were too high during the solar system's formation for volatile materials like water ice and methane to condense. What remained were materials with high melting points, silicates, metals, minerals that could survive the young Sun's fierce radiation. The inner solar system is a realm of rock and metal, worlds with solid surfaces you could stand upon. Beyond Mars, we encounter the asteroid belt, a region where planetary formation failed to produce a full-sized world. Jupiter's gravity, powerful even at this distance, stirred the material in this region, accelerating collisions and preventing accretion into a single body. What remains is a vast collection of rocky debris, hundreds of thousands of objects, ranging from tiny pebbles to Ceres, a dwarf planet nearly 1,000 kilometers across. The asteroid belt marks a transition zone, a boundary between the inner and outer solar system. Past the asteroids, we enter the realm of the giant planets: Jupiter, Saturn, Uranus, Neptune. These worlds formed in the colder outer regions, where ice could condense alongside rock. They captured enormous atmospheres of hydrogen and helium, growing to masses dozens or hundreds of times Earth's. Jupiter alone contains more mass than all the other planets combined. These gas and ice giants dominate the outer solar system gravitationally. Their powerful fields, capturing families of moons and shepherding rings of orbiting material. Beyond Neptune lies another structural feature, the Kuiper Belt, a vast disk of icy objects extending from about 30 to 50 astronomical units from the Sun. This is the realm of Pluto and thousands of similar bodies, worlds made primarily of ice and rock. The Kuiper Belt represents the solar system's third population of small bodies, distinct from both the rocky asteroids and the icy comets. It's a frozen archive of materials left over from planetary formation, preserved in deep cold for 4.6 billion years. What makes the solar system's architecture particularly elegant is how it reflects the conditions during its formation. The material that condensed from the solar nebula was distributed across space according to temperature and composition. Close to the forming sun, only the most refractory materials survived. Further out, progressively more volatile materials could condense. This created distinct compositional zones, each giving rise to different types of worlds. The map of the solar system today is a record of conditions billions of years ago, frozen into orbital architecture. But our map continues to change as new discoveries emerge. In the past 2 decades, we've found that the outer solar system is more populous than we imagined. Hundreds of trans-Neptunian objects have been catalogued, revealing complex dynamics and orbital resonances. We've discovered that some of these distant objects have highly elliptical orbits, suggesting gravitational influences we don't fully understand. There's ongoing debate about whether a massive 9th planet might orbit in the distant outer solar system, unseen but revealed through its gravitational effects on smaller bodies. The solar system's structure also includes the nearly circular orbital plane shared by most planets, a feature called the ecliptic. This flatness isn't coincidence, but consequence. The planets formed from a rotating disk of material, and angular momentum conservation kept most objects orbiting in roughly the same plane. It's why we can draw the solar system as a relatively flat structure rather than a 3-dimensional sphere. Though individual objects have inclined orbits, the overall architecture is remarkably planar, a spinning disk carved by gravity from the chaos of the early solar nebula. As you visualize this structure tonight, imagine seeing it from far above. The sun, a bright point at the center, the planetary orbits, drawn as nested ellipses, the asteroid and Kuiper belts as scattered populations of smaller points. It's a pattern of exquisite regularity, a gravitational architecture that has remained stable for billions of years and will persist billions more. Our home structure, the neighborhood where humanity was born, and from which we're just beginning to venture outward. To understand where the solar system truly ends, we must venture far beyond the planets, past the Kuiper belt, into regions no spacecraft has yet reached, and no human eye will ever see directly. Here, at distances so vast they challenge comprehension, lies the Oort cloud, a theoretical structure that defines the outermost boundary of the sun's gravitational domain. The Oort cloud exists in a realm of profound darkness and cold. At these distances, measured in tens of thousands of astronomical units, the sun appears as merely the brightest star in the sky, offering virtually no warmth. Temperatures hover just a few degrees above absolute zero. Time moves differently here. Objects in the Oort cloud take millions of years to complete a single orbit around the sun. These are the most distant bound objects in the solar system, the last outpost before interstellar space. We've never directly observed the Oort cloud. Its existence is inferred from the behavior of long-period comets, those icy visitors that occasionally plunge into the inner solar system on orbital paths taking thousands or millions of years. The orbits of these comets, when traced backward, originate from all directions around the sun, rather than from a flat disk like the Kuiper belt. This suggests a spherical shell of comet nuclei surrounding the entire solar system, a vast repository of icy bodies left over from planetary formation and gravitationally scattered to these extreme distances by the giant planets. Jan Oort, the Dutch astronomer who proposed this structure in 1950, estimated it might contain trillions of comets. Modern calculations suggest the Oort cloud could hold more mass than Earth, distributed across a volume so enormous it defies visualization. The cloud is thought to begin around 2,000 astronomical units from the sun and extend outward to perhaps 100,000 astronomical units, halfway to the nearest star. It's a structure of almost inconceivable size, a spherical halo of frozen material marking the extreme limit of the sun's gravitational influence. But there's another boundary we must consider, one defined not by gravity, but by the sun's constant outflow of charged particles. The solar wind. This stream of protons and electrons flows outward from the sun's corona at speeds of hundreds of kilometers per second, carrying the sun's magnetic field into space. The solar wind creates a bubble around the sun called the heliosphere, a region of space where the sun's influence dominates over the interstellar medium. The boundary of this bubble is called the heliopause, and unlike the Oort cloud, we've actually crossed it. On August 25, 2012, Voyager 1 became the first human-made object to enter interstellar space, passing beyond the heliopause at a distance of about 122 astronomical units from the Sun. The spacecraft detected a sudden change in its environment. The solar wind stopped, cosmic ray intensity increased, and the magnetic field orientation shifted. Voyager 1 had left the solar bubble and entered the space between stars. Voyager 2 followed on November 5, 2018, crossing the heliopause at a different location and providing our first comparison measurements. What both spacecraft revealed is that the heliopause isn't a perfect sphere, but an irregular boundary, buffeted by the pressure of interstellar wind, distorted by the sun's motion through space. The heliosphere has a long tail, like a comet, streaming behind the sun as it orbits the galaxy. We live inside a teardrop-shaped bubble, moving through the interstellar medium at 70,000 kilometers per hour. Consider the nested boundaries we've described. First the visible planets, then the Kuiper belt marking the edge of the planetary system, then the heliopause where the solar wind ends, and finally the vast Oort cloud extending halfway to the nearest stars. These boundaries don't align. The solar system isn't a single sphere, but a set of overlapping structures, each defined by different physical processes. The Voyager spacecraft, those tiny machines launched in 1977, are now interstellar travelers, coasting through space with no nearby stars to warm them, no gravitational anchor pulling them back. They carry golden records with sounds and images from Earth, messages from a species just learning to map its cosmic neighborhood. In 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese 445. In 300,000 years, it will enter the Oort cloud of another stellar system. These spacecraft are our first ambassadors to the structure beyond our structure, carriers of our curiosity into the vast architecture of stars. As you drift towards sleep tonight, imagine those spacecraft, silent and alone, crossing boundaries we can barely detect from Earth. Imagine the Oort cloud, a sphere of frozen nuclei surrounding our entire planetary system, a structure so large that light takes months to cross it. We're embedded in something vast, something that defines our place in a larger neighborhood. The solar system doesn't end with the planets we can see, but extends outward in layers, each one revealing how our sun's influence gradually gives way to the broader structure of interstellar space. When we venture beyond the solar system's boundaries into true interstellar space, we enter a neighborhood populated by other stars, each with its own heliosphere, possibly its own planetary system, its own Oort cloud. The nearest of these neighbors defines our immediate stellar environment, the local structure we inhabit within the larger galaxy. The closest star to our Sun is Proxima Centauri, a small red dwarf lying 4.24 light-years away. To put that distance in perspective, it means that light traveling at 300,000 kilometers per second takes more than 4 years to cross the space between our stars. If you could somehow travel at the speed of the Voyager spacecraft, the journey would take about 73,000 years. Proxima Centauri is part of a triple star system called Alpha Centauri. The other two components, Alpha Centauri A and B, are Sun-like stars orbiting each other, while Proxima orbits both at a great distance. Within 12 light-years of the Sun, we find 33 stellar systems containing 51 individual stars. Most of these are red dwarfs, small, cool stars, less massive than our Sun. This reflects a universal truth about stellar populations. Small stars vastly outnumber large ones. There are also a few white dwarfs, the collapsed remnants of Sun-like stars that exhausted their nuclear fuel. The nearest of these, Sirius B, orbits the bright star Sirius, the brightest star in Earth's night sky. Astronomers have created detailed three-dimensional maps of our stellar neighborhood, plotting not just the positions of nearby stars, but their motions through space, their spectral types, their ages. These maps reveal that stars aren't randomly distributed. Some cluster together, moving through space as groups. Others, like our Sun, are more isolated. Our nearest neighbors are scattered across 3 dimensions, creating a complex architecture of gravitational influence and empty space. But our stellar neighborhood exists within a larger structure called the local bubble. And understanding this feature reveals something profound about how the galaxy organizes itself at multiple scales. The local bubble is a cavity in the interstellar medium, a region of space about 1,000 light-years across, where the gas between stars is much hotter and more diffuse than average. We're located near the edge of this bubble, residing in a slightly denser region called the local fluff or local cloud. How did this bubble form? The answer lies in one of the most violent phenomena in the cosmos, supernovae. When massive stars reach the end of their lives, they explode with such tremendous energy that they blast away the surrounding interstellar gas, creating cavities hundreds of light years across. The local bubble was carved by a series of supernovae that occurred in this region over the past 10 to 20 million years. These explosions swept the local interstellar medium clear of cool gas, leaving behind a hot, tenuous plasma that fills the bubble. The bubble's walls, where the expanding blast waves have compressed the interstellar medium, are sites of active star formation. When you compress gas in space, it can trigger gravitational collapse and the birth of new stars. So supernovae don't just destroy, they also create, shaping the galactic structure and potentially seeding new generations of stellar formation. We live inside a structure created by stellar death, surrounded by walls where stellar birth is occurring. Recent studies using data from the Gaia Space Telescope have revealed the 3-dimensional structure of the local bubble with unprecedented clarity. Astronomers can now map the positions and velocities of hundreds of thousands of stars in our neighborhood, seeing how they move in relation to the bubble's walls, identifying which stars likely formed in the shell of compressed gas. The Sun itself is moving through the bubble, currently passing through a small cloud of slightly denser material within the larger cavity. This nesting of structures is characteristic of the galaxy. We exist within a solar system, which exists within a stellar neighborhood, which exists within the local bubble, which exists within a spiral arm of the Milky Way. Each level of structure influences the others. The local bubble affects where stars form in our neighborhood, which affects planetary system formation, which affects the prospects for life. Structure at one scale shapes possibilities at other scales. Our maps of the stellar neighborhood continue to improve as new surveys discover previously unknown nearby stars. Brown dwarfs, objects too small to sustain hydrogen fusion and therefore very faint, likely populate the space around us in numbers we're only beginning to appreciate. Some of the nearest objects to our Sun might still await discovery, hidden by their faintness and the difficulty of detecting such dim sources. The complete map of our neighborhood remains a work in progress. As you visualize the stellar neighborhood tonight, imagine our Sun as one point of light among many, surrounded by dozens of nearby stars scattered through 3-dimensional space. Imagine the local bubble as a vast cavity containing all these stars, its walls glowing faintly from ongoing star formation, its interior filled with hot, thin gas left by ancient supernovae. We inhabit a pocket of unusual space within the galaxy, a bubble in the cosmic foam, and our maps are revealing its structure star by star, cloud by cloud, with increasing precision and beauty. To map our galaxy is to attempt something paradoxical, creating a picture of a structure we can never step outside to view. Every image you've seen of the Milky Way's spiral arms is either an artist's interpretation based on data or a photograph of a different galaxy that resembles our own. We're embedded within our galaxy, positioned about halfway out from the center, trying to infer the shape of a structure 100,000 light-years across from our single vantage point inside it. The Milky Way is a barred spiral galaxy, a classification that describes its fundamental architecture. At the center lies a dense spherical bulge of old stars surrounding a supermassive black hole with a mass of about 4 million suns. This black hole, called Sagittarius A, pronounced Sagittarius A star, sits precisely at the gravitational center of our galaxy, though it represents only a tiny fraction of the galaxy's total mass. Extending from the central bulge is a bar-shaped structure made of stars, about 27,000 light-years long, rotating as a coherent feature. From the ends of this bar, spiral arms emerge and wrap around the galaxy in a pattern that's still being mapped and debated. We've identified several major arms: the Perseus arm, the Scutum Centaurus arm, the Norma arm, and the Sagittarius arm. There are also smaller features called spurs or feathers, less prominent structures that connect or branch between major arms. Our Sun resides in one of these minor features, the Orion spur, sometimes called the Orion arm, positioned between the Perseus and Sagittarius arms. Mapping these spiral arms is extraordinarily difficult. The challenge lies in determining distances across the galactic plane while we're embedded within it. Astronomers use multiple techniques: measuring parallax of nearby stars, observing variable stars with known intrinsic brightness, mapping regions of ionized hydrogen that trace star formation, and analyzing the velocities of molecular clouds using radio telescopes. Each method has limitations and uncertainties. The resulting maps often disagree on details, though the broad structure is becoming clearer. What causes spiral structure? For decades, astronomers debated whether spiral arms were material structures, like grooves in a record, or wave patterns passing through the galaxy's disk. The current understanding is that they're density waves, regions where the concentration of stars and gas temporarily increases as material orbits through them. Think of a traffic jam on a highway. Cars slow down as they pass through the jam, increasing density in that region, but the jam itself moves at a different speed than the individual cars. Similarly, spiral arms are regions of increased stellar density that rotate at a different speed than the stars themselves. This density wave pattern has profound implications for star formation. When gas clouds enter a spiral arm, they experience increased density and pressure, triggering gravitational collapse and the birth of new stars. The youngest, hottest, brightest stars therefore concentrate in spiral arms, making the arms visible in photographs of other galaxies. But these massive stars are short-lived. By the time their orbits carry them out of the arm where they formed, they've already died, often in supernova explosions that trigger new waves of star formation. The spiral arms appear bright because they're sites of continuous stellar birth and death. Our galaxy's disk, the flat structure containing the spiral arms, is remarkably thin relative to its width. The disk stretches about 100,000 light-years across, but only about 1,000 light-years thick in the midplane where we reside. This extreme flatness results from angular momentum. The original cloud that collapsed to form the Milky Way was rotating, and rotation prevents collapse in the plane perpendicular to the spin axis. The result is a flattened, rotating disk, a structure that emerges naturally whenever rotating material collapses under gravity. But the disk isn't perfectly flat. Recent observations have revealed that the outer regions of the galactic disk warp and flare, bending up on one side and down on the other, like the brim of a floppy hat. This warping might result from gravitational interactions with satellite galaxies or from the galaxy's dark matter halo, having a slightly different shape than the visible disk. The Milky Way structure is more complex than simple models suggested, full of asymmetries and irregularities that make mapping it more challenging and more interesting. Surrounding the disk is the galactic halo, a roughly spherical region containing old stars and globular clusters. These ancient stars, some nearly as old as the universe itself, orbit the galaxy in elliptical paths that carry them far above and below the disk. The halo represents the first generation of stars that formed when our galaxy was young. Most of the halo's mass, however, isn't in stars but in dark matter, the invisible component that provides the gravitational glue holding the entire galaxy together. Our position in the Orion Spur, about 26,000 light-years from the galactic center, takes approximately 230 million years to complete one orbit. The last time the Sun was at this position in its galactic orbit, dinosaurs had just begun to appear on Earth. Every aspect of human history, every civilization that has risen and fallen, has occurred within a tiny fraction of a single galactic rotation. We're cosmic newcomers, just beginning to map the structure that gave us birth. As you drift towards sleep, imagine our galaxy as it might appear from outside. A vast pinwheel of stars rotating in the darkness, spiral arms traced in the light of young stars. The central bar rotating like a spoke, and our small sun embedded in a minor arm, one tiny point among hundreds of billions. The Milky Way is our larger neighborhood, the structure within which our solar system and stellar neighborhood exist. We're mapping it slowly, carefully, building a picture of something magnificent that we can only see from inside. The Milky Way doesn't exist in isolation. Our galaxy is accompanied by a family of smaller satellite galaxies, and together with our nearest large neighbor, the Andromeda Galaxy, we form a structure called the local group. Understanding this structure requires zooming out beyond a single galaxy and mapping the architecture of our cosmic locality. The most prominent of our satellite galaxies are the large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere as misty patches that ancient navigators used for wayfinding. The Large Magellanic Cloud lies about 163,000 light-years from the Milky Way and contains roughly 30 billion stars. The Small Magellanic Cloud, at about 200,000 light-years distant, holds around 3 billion stars. Both are irregular dwarf galaxies, lacking the spiral or elliptical structure of larger galaxies, instead appearing as loosely organized collections of stars, gas and dust. Recent observations have revealed that the Magellanic Clouds are actually connected to each other and to the Milky Way by vast streams of gas called the Magellanic Stream. This structure, discovered in the 1970s through radio observations of neutral hydrogen, stretches across more than 180 degrees of sky. It represents material stripped from the satellite galaxies by the Milky Way's gravitational influence, a visible record of galactic interaction playing out over billions of years. But the Magellanic Clouds are just the largest and most obvious of our satellites. Modern surveys have discovered dozens of dwarf galaxies orbiting the Milky Way. Most are tiny, containing just thousands or millions of stars, and are dominated by dark matter. These ultra-faint dwarf galaxies are among the darkest structures in the universe. Galaxies like Segue 2 and Willman 1 contain so few stars they're barely distinguishable from globular clusters, yet their stars move so fast they must be embedded in massive dark matter halos. The distribution of satellite galaxies around the Milky Way presents puzzles that challenge our understanding of structure. Formation. Computer simulations of galaxy formation predict hundreds of satellite galaxies should orbit a Milky Way-sized galaxy, yet we've found only about 60. This discrepancy, called the missing satellites problem, suggests either that many satellites are too faint to detect, or that our models of dark matter and structure formation need revision. Roughly 2.5 million light-years from the Milky Way lies Andromeda, catalogued as M31, a spiral galaxy larger than our own. Andromeda contains perhaps 1 trillion stars, compared to the Milky Way's few hundred billion. Like the Milky Way, Andromeda has its own family of satellite galaxies, including M32 and M110, visible in backyard telescopes, and dozens of fainter dwarfs discovered in recent surveys. Andromeda and the Milky Way are approaching each other at about 110 kilometers per second. This motion is unusual because the overall expansion of the universe causes most distant galaxies to recede from us. But gravitationally bound structures, like the local group, aren't expanding with the universe. Instead, the two large galaxies are falling toward each other, pulled by their mutual gravitational attraction. In about 4.5 billion years, they will collide and merge, creating a single, giant elliptical galaxy that astronomers have playfully named Milkomeda. The local group contains about 80 known galaxies spread across a volume roughly 10 million light-years across. Besides the Milky Way and Andromeda, the only other large member is the Triangulum Galaxy, M33, a spiral galaxy about 60,000 light-years across, lying about 3 million light-years away. The remaining members are dwarf galaxies, some orbiting the large spirals as satellites, others existing independently in the space between. The mass that defines the local group's structure is mostly invisible. Observations of how the member galaxies move reveal that the group contains about 50 times more dark matter than visible matter. This dark matter provides the gravitational scaffolding that organize the local group's formation and continues to influence the orbits of its members. The visible galaxies we map are merely the bright points in a much larger dark matter architecture. Modern surveys are still discovering new members of the local group, particularly ultra-faint dwarf galaxies that require the largest telescopes to detect. Each discovery helps refine our map of this structure and our understanding of how small galaxies form and evolve. The local group is both our gravitational home and our cosmological laboratory, close enough to study in detail, yet large enough to represent typical structures in the larger universe. The local group exists at an interesting threshold in cosmic structure. It's large enough to be significantly affected by dark matter and to show complex gravitational interactions, yet small enough that expansion hasn't separated its members beyond gravitational binding. We can map it comprehensively in a way that's impossible for larger structures. It's our immediate neighborhood in the hierarchy of cosmic organization. As you visualize the local group tonight, imagine two large spiral galaxies, the Milky Way and Andromeda, slowly approaching through space, each surrounded by a swarm of smaller satellites, with Triangulum and dozens of dwarf galaxies scattered through the volume between. The whole structure is bound together by gravity, a gravitational island in the expanding universe, our local cosmic village. We're mapping this structure with increasing precision, discovering new neighbors, tracking their motions, understanding how this local architecture formed, and how it will evolve over billions of years to come. Everything we've mapped so far, every structure we've described from planets to galaxies, represents only a small fraction of the matter that shapes cosmic architecture. The universe's largest structures are built on an invisible foundation, dark matter, a form of matter that neither emits nor absorbs light, revealing itself only through gravitational influence. To truly map the universe, we must chart what we cannot see. The evidence for dark matter appears at every scale we examine. Within galaxies, stars orbit faster than they should based on the mass of visible matter alone. The orbital speeds of stars in the outer regions of spiral galaxies should decrease with distance from the center if visible matter dominates. Much like planets in the solar system, orbit slower the farther they are from the sun. But observations show that rotation speeds remain constant or even increase in outer regions, implying enormous quantities of unseen mass extending far beyond the visible disk. Galaxy clusters provide even more compelling evidence. When Fritz Zwicky studied the Coma cluster in the 1930s, he measured the velocities of member galaxies and found they were moving so fast the cluster should fly apart unless it contained far more mass than visible light revealed. Zwicky called this unseen component Dunkel Materia, dark matter. His calculations suggested the cluster contained 400 times more dark matter than visible matter. Modern estimates place the ratio closer to 50-1, still a dramatic dominance of the invisible. Perhaps the most beautiful evidence comes from gravitational lensing, a phenomenon predicted by Einstein's general relativity. Massive objects curve space-time, bending the path of light passing nearby. When a massive galaxy cluster lies between Earth and more distant galaxies, the cluster's gravity acts as a lens, distorting the images of background galaxies into arcs and multiple images. By analysing these distortions, astronomers can map the cluster's mass distribution, including dark matter. The resulting maps reveal that dark matter forms smooth halos around galaxies and clusters, providing the gravitational potential wells in which visible matter collects. What is dark matter made of? Despite decades of searches, we still don't know. It's not ordinary matter made of protons and neutrons. It doesn't interact with light or electromagnetic fields. It appears to interact only through gravity, and possibly through the weak nuclear force. The leading hypothesis is that dark matter consists of unknown particles left over from the Big Bang, perhaps weakly interacting, massive particles, WIMPs, or axions. Despite enormous experimental efforts to detect these particles directly, they remain elusive, known only by their gravitational fingerprints. Computer simulations have revealed how dark matter shapes structure formation. In these simulations, dark matter begins as tiny quantum fluctuations in the early universe. As space expands, these fluctuations grow through gravitational instability, pulling in more dark matter and forming increasingly dense regions. The dark matter collapses into a cosmic web of filaments and halos, while ordinary matter, which can radiate energy and cool, condenses within the dark matter potential wells to form stars and galaxies. The structure of dark matter halos follows predictable patterns. At the largest scales, halos are nearly spherical. At smaller scales, they show complex substructure with smaller halos orbiting within larger ones. Every galaxy exists within a dark matter halo, extending far beyond the visible stars. The Milky Way's dark matter halo probably extends 600,000 light-years from the galactic center, more than 6 times the diameter of the visible disk. We live embedded in dark matter, passing through it constantly, yet we feel only its collective gravitational effect, not the individual particles. Recent observations have revealed a puzzling asymmetry between computer simulations and observations of dark matter halos. Simulations predict that halos should contain many dense subhalos and should have dense centers. But observations suggest actual halos are smoother and less centrally concentrated than models predict. This discrepancy, sometimes called the core cusp problem, hints that we might misunderstand dark matter's properties or the physics governing structure formation. Dark matter is also crucial for understanding why any structure exists at all. In the early universe, ordinary matter was too hot and radiation pressure too strong for gravitational collapse to occur. But dark matter, immune to radiation pressure, began collapsing earlier, creating gravitational potential wells into which ordinary matter could later fall. Without dark matter providing this initial scaffolding, galaxies might never have formed. The cosmic structures we map owe their existence to invisible architecture. Mapping dark matter requires indirect methods. Besides gravitational lensing, astronomers use the rotation curves of galaxies, the velocities of galaxies in clusters, and observations of the cosmic microwave background radiation. Each technique probes dark matter at different scales. When combined, these observations reveal a consistent picture: dark matter outmasses ordinary matter by a factor of about 5 to 1, and it provides the gravitational framework upon which all cosmic structure builds. The cosmic web we'll explore in the next chapters is fundamentally a dark matter web, with visible galaxies marking the densest nodes and filaments. When we map the universe's largest structures, we're really mapping where dark matter is concentrated over billions of years. The luminous galaxies are merely tracers of underlying dark architecture, bright beacons illuminating the scaffolding that gives the universe its shape. As you contemplate this tonight, consider that you're surrounded by dark matter. A stream of dark matter particles might be flowing through your room right now, through the earth, through your body, completely oblivious to ordinary matter. We exist within a dark matter halo that makes our galaxy possible. Most of the universe's structure is invisible, known only through its gravitational influence. The map we're creating must account for what we cannot see, charting the invisible foundation that supports everything visible. As we zoom out beyond the local group, the universe's structure becomes increasingly dramatic. Individual galaxies gather into clusters, and clusters themselves organize into superclusters, creating a hierarchy of structures that extends across hundreds of millions of light years. We're mapping the universe's largest gravitationally bound systems and discovering how they connect to form something even larger. The nearest major galaxy cluster to the local group is the Virgo cluster, lying about 54 million light-years away in the direction of the constellation Virgo. This cluster contains over 1,500 galaxies spread across a region about 15 million light-years in diameter. At its center lies M87, a giant elliptical galaxy containing trillions of stars and hosting a supermassive black hole of 6.5 billion solar masses, the first black hole ever directly imaged by the Event Horizon Telescope in 2019. The Virgo cluster dominates our cosmic neighborhood gravitationally. Even though the local group itself is a bound structure, the entire local group is falling toward Virgo, pulled by the cluster's enormous mass. Our motion through space includes not just the expansion of the universe and our orbit around the Milky Way, but also this large-scale flow toward the nearest major cluster. The local group will eventually merge with the Virgo cluster, though this process will take many billions of years. Galaxy clusters are enormous structures, typically containing hundreds to thousands of galaxies and masses equivalent to hundreds of trillions of suns. But the galaxies themselves constitute only about 2% of a cluster's mass. Another 13% exists as hot gas filling the space between galaxies, heated to tens of millions of degrees and radiating X-rays. This intra-cluster medium is one of the most extreme environments in the universe, with densities far lower than any vacuum achievable on Earth, yet temperatures exceeding those in stellar interiors. The remaining 85% of cluster mass is dark matter. The dark matter halos of individual galaxies merge into a single, enormous cluster halo, creating the gravitational potential well that holds everything together. Mapping this dark matter through gravitational lensing reveals smooth distributions that peak at cluster centers and gradually decline outward, providing the scaffolding upon which visible structures rest. Within clusters, galaxies move at tremendous speeds, often exceeding 1,000 kilometers per second. These high velocities should scatter galaxies apart, unless the cluster contains enormous mass to gravitationally bind them. This was precisely Zwicky's insight in the 1930s when studying the Coma cluster. The visible galaxies moved too fast to remain bound by their own visible mass. Something invisible must dominate the cluster's gravitational budget. Clusters themselves organize into superclusters, enormous complexes spanning hundreds of millions of light years. The Virgo cluster is part of the Virgo supercluster, also called the local supercluster, a structure containing about 100 galaxy groups and clusters, including our local group. For decades, astronomers believed the Virgo supercluster represented our largest gravitationally associated structure. But in 2014, new mapping techniques revealed something surprising. By charting the peculiar velocities of galaxies, their motion relative to the cosmic expansion, astronomer Brent Tully and colleagues discovered that the Virgo supercluster is itself part of a much larger structure they named Laniakea, which means immense heaven in Hawaiian. This discovery forced a complete revision of our cosmic address and our understanding of supercluster boundaries. Superclusters represent the transition between structures that are gravitationally bound and those that are merely density enhancements in the expanding universe. The galaxies within a supercluster share some common motion, but the structure as a whole is typically not dense enough to have collapsed into a single gravitationally bound object. Instead, superclusters are associations, regions where galaxy clusters are more numerous than average, embedded in the larger pattern called the cosmic web. The architecture of galaxy clusters reveals the history of structure formation. Clusters grow by merging with smaller groups and by accreting individual galaxies from surrounding space. Many clusters show evidence of recent mergers, disturbed X-ray emission from the hot gas, subclusters in the process of merging, shockwaves visible in multi-wavelength observations. The Bullet cluster, formed by the collision of two galaxy clusters, provided some of the most compelling evidence for dark matter when observations showed the cluster's dark matter halos passing through each other while the hot gas collided and slowed. Modern surveys are cataloguing galaxy clusters across the observable universe. The Sloan Digital Sky Survey, the 2DF Galaxy Redshift Survey, and successor programs have mapped millions of galaxies and identified tens of thousands of galaxy groups and clusters. These maps reveal how cluster density varies with cosmic time, providing crucial tests of our cosmological models and our understanding of dark energy's effects on structure growth. Rich galaxy clusters also serve as cosmological laboratories. Their properties depend on the universe's density, the nature of dark energy, and the initial spectrum of density fluctuations. By studying how the abundance of galaxy clusters changes with cosmic time, and how massive the most extreme clusters become, cosmologists constrain fundamental parameters describing our universe's evolution and ultimate fate. As you visualize cosmic structure at this scale, imagine galaxy clusters as bright knots in a vast three-dimensional tapestry, each knot containing hundreds or thousands of galaxies embedded in dark matter halos and bathed in hot X-ray emitting gas. These knots don't scatter randomly, but follow patterns, concentrating along filaments and sheets while avoiding vast empty regions called voids. The clusters are markers, bright signposts illuminating the underlying cosmic architecture. We're mapping these structures by conducting spectroscopic surveys of millions of galaxies, measuring their distances through redshift, plotting their three-dimensional positions, and identifying concentrations that mark clusters and superclusters. The resulting maps reveal a universe organized on the largest scales into a foam-like structure, a pattern simultaneously random and regular, chaotic and elegant, that we're only beginning to fully comprehend. The largest structures in the universe aren't spherical clusters, but elongated filaments and walls, vast collections of galaxies stretching across hundreds of millions of light years. These structures define the cosmic web, the dominant pattern of organization at the largest scales. Mapping them reveals the universe's fundamental architecture. In 1989, Margaret Geller and John Huchrer of the Harvard-Smithsonian Center for Astrophysics announced the discovery of the Great Wall, a structure so immense it challenged existing theories of structure formation. By mapping the three-dimensional positions of galaxies in a narrow slice of sky, they revealed a coherent structure extending more than 500 million light-years across, containing tens of thousands of galaxies arranged in a sheet-like formation. At the time, it was the largest known structure in the universe. The Great Wall isn't alone. Subsequent surveys have discovered even larger filamentary structures. The Sloan Great Wall, identified in 2003, extends approximately 1.38 billion light-years. The Huge Large Quasar Group, a collection of 73 quasars, spans about 4 billion light-years, though whether this represents a true, coherent structure remains debated. With each new survey, we discover that the universe organizes itself into structures at scales we previously thought impossible. These filaments aren't mere alignments of galaxies, but represent regions where dark matter and ordinary matter have concentrated over cosmic history. The filaments are like cosmic highways, channels along which galaxies move and where gas flows. Most galaxies, including our own, don't reside in rich clusters, but along these filaments, in the suburbs of cosmic structure rather than its downtown cores. The formation of filaments traces back to the earliest moments of the universe. Tiny quantum fluctuations in the density of matter during the Big Bang, amplified by cosmic inflation, created regions slightly denser and slightly less dense than average. Denser regions attracted more matter through gravity and grew denser still. But this collapse didn't occur uniformly in all directions. The geometry of the initial fluctuations and the dynamics of gravitational instability caused matter to collapse first into sheets, then into filaments, and finally into compact clusters at the intersections of filaments. Computer simulations of cosmic structure formation reproduce this pattern beautifully, starting with initial conditions matching the fluctuations observed in the cosmic microwave background. Simulations evolve forward in time under gravity and the expansion of the universe. What emerges is a cosmic web of filaments and sheets surrounding vast empty regions. The simulated webs match the structures we observe in galaxy surveys with remarkable fidelity, providing strong confirmation that we understand the basic physics of structure formation. The filaments themselves have structure at multiple scales. The largest filaments contain smaller filaments, which contain smaller still, in a hierarchical pattern extending down to individual galaxies. This self-similar structure reflects the scale-free nature of gravitational collapse. The same physics that creates galactic structure creates filaments, just operating across vastly different scales and timescales. Matter flows along filaments toward the densest nodes where galaxy clusters form. This accretion continues today. Telescopes observing in specific wavelengths can detect cold gas streaming along filaments into galaxy clusters, fuel for future star formation. The filaments are not static structures, but dynamic conduits, channeling material from underdense regions toward overdense ones, participating in the ongoing evolution of cosmic structure. The geometry of the cosmic web has profound implications for galaxy evolution. Galaxies in dense cluster environments differ from those in filaments or isolated in voids. Cluster galaxies tend to be redder, older, and lacking in gas compared to field galaxies. This reflects environmental effects, galaxy collisions, harassment from near passes, and ram pressure stripping as galaxies move through. Hot intra-cluster gas all transform galaxies in dense environments. The position of a galaxy within cosmic structure influences its entire evolutionary history. Mapping filaments requires three-dimensional surveys covering vast volumes of space. Modern surveys like the Sloan Digital Sky Survey have measured spectra and distances for millions of galaxies, creating three-dimensional maps that reveal the cosmic web directly. When these galaxies are plotted in 3 dimensions, the filamentary pattern becomes immediately apparent, a nested hierarchy of structures connecting clusters and spanning voids. But most of the mass in filaments remains invisible. The dark matter that gravitationally defines filaments doesn't emit light. The ordinary matter exists mostly as diffuse gas, too cool to radiate efficiently. Only where gas has condensed into stars and galaxies do we see the filaments directly. We're mapping a structure through its brightest features, recognizing that most of its mass eludes direct detection. The extent of filamentary structure poses challenges for cosmological theory. When the first Great Wall was discovered, its size exceeded what models predicted should form by the present epoch. Subsequent discoveries of even larger structures have continued to push theoretical boundaries. While most cosmologists believe these structures are consistent with our cosmological model, they represent extreme examples of structure formation that test the limits of what's predicted. Filaments also affect the cosmic radiation field. As light from distant quasars travels through filaments, it encounters greater densities of neutral hydrogen, creating absorption features that reveal the filament's presence. This technique, called the Lyman alpha forest, allows astronomers to map filamentary structure across cosmic time by observing distant light sources through intervening structure. As you imagine the cosmic web tonight, visualize it as a three-dimensional foam with filaments forming the edges where surfaces meet, sheets forming the faces, and voids occupying the interior bubbles. Galaxy clusters mark the nodes where multiple filaments intersect. Our Milky Way resides along one such filament, part of the Laniakea Superclusters structure, moving through space along paths defined billions of years ago by the initial distribution of matter in the early universe. We're mapping these structures across billions of light years, observing light that left distant galaxies billions of years ago, reconstructing the cosmic web's evolution across cosmic time. The pattern we see today developed over nearly 14 billion years of gravitational evolution, transforming tiny initial fluctuations into the magnificent architecture we observe stretching across the cosmos. Between the filaments and walls, occupying most of the universe's volume, lie the cosmic voids, vast regions of profound emptiness that are as important to cosmic structure as the dense regions we've described. To map the universe completely, we must chart not just where matter concentrates, but where it's conspicuously absent. The first major void was discovered in 1981 by Robert Kirshner and colleagues while mapping galaxy positions in the direction of the constellation Bootes. They found a spherical region approximately 330 million light-years in diameter, containing very few galaxies, perhaps 60, where hundreds would be expected. The Bootes void, sometimes called the Great Nothing, showed that underdense regions exist at enormous scales, matching the overdense structures like clusters and filaments. Subsequent surveys have revealed that voids are not rare but characteristic. Approximately 80% of the universe's volume is occupied by voids. These regions aren't completely empty. They contain some isolated galaxies and diffuse dark matter and gas, but at densities far lower than cosmic average. If cosmic structure resembles a sponge or foam, voids constitute the air pockets, the empty spaces that give structure its texture. Voids are typically bounded by walls and filaments, where galaxies concentrate. The voids themselves are roughly spherical or ellipsoidal, though they can have complex irregular shapes where multiple voids meet. Their sizes range from tens of millions to hundreds of millions of light years. The largest known voids approach 1 billion light years across, though identifying coherent structures at such scales becomes challenging given the finite size of survey volumes. The few galaxies that do exist within voids differ from those in denser environments. Void galaxies tend to be small, blue, and actively forming stars. They haven't experienced the collisions, mergers, and environmental effects that transform galaxies in clusters. Void galaxies represent a relatively pristine population, evolving in isolation, providing insights into galaxy formation and evolution in the absence of strong environmental influences. The existence of voids traces back to the same initial density fluctuations that created filaments and clusters. Regions that were slightly underdense in the early universe remained underdense, or became more so as gravity pulled matter out of them toward neighbouring overdense regions. As dense regions collapsed into filaments and clusters, underdense regions expanded, creating larger and emptier voids. The expansion of the universe stretches voids, making them larger over time, while dense regions resist expansion through gravitational binding. Computer simulations show void formation naturally arising from gravitational structure formation. The same models that reproduce the cosmic web of filaments also produce voids of the observed sizes and shapes. In simulations, voids appear as interconnected cells, like bubbles in foam, separated by sheets and filaments of matter. The comparison to foam isn't mere metaphor, but an accurate description of the cosmic web's topology. The interiors of voids are among the most tranquil environments in the universe. Densities are lower, gravitational force is weaker, and the expansion of the universe less impeded by matter. Some cosmologists have suggested that voids might expand faster than the cosmic average, though this remains debated. Measurements of cosmic expansion in different environments could reveal how dark energy's effects vary with density. Voids also serve as cosmological probes. Their size distribution and evolution provide tests of cosmological models independent of those based on galaxy clusters or the cosmic microwave background. The growth of voids over cosmic time depends on the universe's matter density and the properties of dark energy. By comparing void sizes at different redshifts, cosmologists can constrain these fundamental parameters. One of the most peculiar aspects of voids is their regularity. Despite forming from random initial fluctuations, voids show a characteristic size scale. This regularity reflects the underlying physics. There's a natural scale set by the density of matter and the expansion rate at which voids form and grow. The distribution of void sizes follows predictable statistical patterns, another success of our cosmological models. The question of whether we live in a void has been raised and investigated. If the Milky Way were located in a significant underdensity, this could affect our interpretation of cosmological observations, potentially explaining some anomalies without invoking dark energy. However, surveys of our local environment show we're not in a significant void. Our local group resides in a modestly dense environment, along a filament rather than in a void's interior. Mapping voids requires three-dimensional surveys covering large volumes. Two-dimensional projections on the sky can't reveal voids since projected images superimpose near and far structures. Only by measuring distances and constructing three-dimensional maps do voids appear as coherent empty regions. Modern redshift surveys have catalogued thousands of voids, creating comprehensive maps of both the dense and empty aspects of cosmic structure. Recent studies have discovered supervoids, regions even emptier and larger than typical voids. The Eridanus supervoid, stretching across approximately 1 billion light-years, may be associated with a mysterious cold spot in the cosmic microwave background radiation. While the connection remains uncertain, it suggests that the largest voids might have measurable effects on radiation passing through them, offering another tool for studying these enigmatic structures. As you contemplate cosmic voids tonight, recognize them not as absences or failures of structure, but as integral components of cosmic architecture. The voids define the structure as much as the filaments and clusters. Without voids, there would be no cosmic web, no organized structure at the largest scales. The universe's architecture is as much about where matter isn't as where it is. Imagine yourself floating in the center of a void, hundreds of millions of light-years from the nearest significant concentration of galaxies. In every direction, darkness extends for dozens of millions of light-years before you encounter the void's boundary walls. The expansion of space is proceeding almost unimpeded, stretching the already vast emptiness larger. It's one of the loneliest places in the cosmos, a cathedral of emptiness. Yet even here, the universe's structure remains present in the very absence of matter. For decades, astronomers believed our cosmic address ended with the Virgo supercluster, a structure containing the local group, the Virgo cluster, and about 100 other galaxy groups and clusters spread across roughly 110 million light-years. This was the largest structure we thought we belonged to, our place in the cosmic hierarchy. Then in 2014, everything changed when a team led by Brent Tully used a new mapping technique that revealed we'd been dramatically underestimating the scale of our cosmic neighborhood. The breakthrough came from mapping peculiar velocities, the motion of galaxies relative to the overall expansion of the universe. While cosmic expansion carries galaxies apart, gravity pulls them toward regions of higher density. By carefully measuring both the recession velocities from expansion and the additional motions caused by gravitational attraction, astronomers can trace the flow of galaxies through space and identify the gravitational basins they're flowing toward. What Tully's team discovered was astonishing. The Virgo supercluster, which we thought represented our largest gravitational association, is actually just one lobe of a vastly larger structure. Galaxies across a region 520 million light-years in diameter all share a common motion, flowing along gravitational pathways toward a central basin. This immense structure contains the mass of about 100,000 trillion suns, distributed among roughly 100,000 galaxies. Tully named it Laniakea, Hawaiian for immense heaven. The discovery fundamentally changed how we understand superclusters. Previously, superclusters were defined by overdensities in galaxy distribution, regions where clusters appeared more concentrated than average. But this definition was somewhat arbitrary, depending on where you drew boundaries. Laniakea is defined instead by dynamics, by the actual motion of galaxies. Its boundary marks the watershed where galaxies begin flowing toward neighboring basins rather than toward Laniakea's center. At the heart of Laniakea lies the Great Attractor, a gravitational anomaly that astronomers had known about since the 1970s but struggled to understand. The Great Attractor is a region of unusually high mass concentration in the direction of the constellations Hydra and Centaurus, located about 150 million light-years away. Our local group, along with everything else in Laniakea, is flowing toward this region at about 600 kilometers per second on top of our motion from cosmic expansion. But the Great Attractor itself isn't the deepest point in Laniakea's gravitational well. That distinction belongs to the Norma cluster, an even more massive concentration partially hidden behind the dust and stars of our own galaxy's disk. The zone of avoidance, as this obscured region is called, has made mapping this crucial part of our supercluster extraordinarily difficult. We're trying to map our cosmic neighborhood while a significant portion of it is blocked from view. Laniakea's structure resembles a vast branching system, like the watershed of a great river. Galaxies flow along filamentary channels, merging into larger streams that converge toward the central basin. The Virgo supercluster forms one major branch. The Hydra-Centaurus supercluster forms another. The Pavo-Indus supercluster contributes a third flow. All these streams merge in the region around the Great Attractor, creating a coherent pattern of motion across hundreds of millions of light-years. The discovery of Laniakea revealed that cosmic structure extends to larger scales than we'd appreciated. But it also showed that Laniakea itself isn't alone. Neighboring superclusters like Perseus Pisces and Coma lie beyond Laniakea's boundaries, separated by regions where galaxies flow toward different gravitational centers. The universe contains many Laniakea-scale structures, each a distinct basin in the cosmic landscape. Understanding Laniakea required new observational techniques. Measuring peculiar velocities accurately demands precise distance measurements, something that became possible only with large surveys using methods like the Tully-Fisher relation for spiral galaxies and the fundamental plane for ellipticals. These techniques allow astronomers to determine a galaxy's distance independent of its redshift, revealing the additional motion beyond cosmic expansion. The maps that emerged from this work are among the most beautiful in astronomy. Visualizations show galaxies as points colored by their velocity, arrows indicating direction of motion, streamlines tracing the flow toward gravitational centers. The resulting image looks organic, almost biological, like blood flowing through vessels or rivers converging into a delta. The universe's large-scale structure reveals itself not as static architecture, but as dynamic flow. Laniakea's existence has implications for our cosmological understanding. The fact that such large structures exist and show coherent motion provides tests of our models of structure formation and dark energy. The growth of structures this large depends on the universe's matter content and expansion history. Laniakea is both our home supercluster and a cosmic laboratory where we can study structure formation at the largest scales. Our motion through Laniakea also affects our observations of the cosmic microwave background. The CMB appears slightly hotter in the direction we're moving and slightly cooler in the opposite direction, a dipole pattern caused by our motion through the universe. By measuring this dipole precisely, we can determine our total velocity, including our motion, through Laniakea. We're moving at about 370 kilometers per second relative to the CMB rest frame. As you contemplate Laniakea tonight, recognize that every galaxy you can see in the night sky, every distant light that reaches your eye, is part of this vast structure. We're embedded in something immense, a gravitational basin that shapes the motion of 100,000 galaxies across 500 million light-years. The discovery of Laniakea reminds us that the universe continues to reveal structure at scales we hadn't imagined, that our cosmic address keeps expanding as our maps improve. Imagine standing back far enough to see Laniakea whole, a vast web of galaxies flowing along filaments toward a central concentration, the entire structure embedded in dark matter scaffolding, slowly evolving under gravity's patient influence. We're residents of this immense heaven, participants in its gravitational dance, mapmakers charting the currents that carry us through cosmic space. To understand the largest structures in the universe and how they formed, we must look at the oldest light we can observe, radiation that has traveled through space for nearly 14 billion years. The cosmic microwave background is a photograph of the infant universe, a map of tiny temperature variations that would eventually grow into galaxies, clusters, and superclusters. It's simultaneously our most distant observation and our most important guide to understanding cosmic structure. The cosmic microwave background, often abbreviated CMB, is the afterglow of the Big Bang itself. About 380,000 years after the universe began, space had expanded and cooled enough for electrons and protons to combine into neutral hydrogen. Before this moment, the universe was an opaque plasma where photons constantly scattered off charged particles. After recombination, photons could travel freely through space. The CMB is this ancient light, stretched by cosmic expansion from visible wavelengths to microwaves, reaching us today from every direction in the sky. When the CMB was first discovered accidentally in 1964 by Arno Penzias and Robert Wilson, it appeared perfectly uniform, the same temperature in every direction. But astronomers predicted it should show tiny variations, imprints of density fluctuations in the early universe. Finding these variations became one of astronomy's great quests, requiring satellites above Earth's atmosphere to detect microwave radiation without interference. The breakthrough came in 1992 when NASA's Cosmic Background Explorer satellite, COBE, detected temperature variations of about 1 part in 100,000 across the sky. The universe at 380,000 years old wasn't perfectly uniform, but showed tiny hot and cold spots. These variations, though minute, were revolutionary. They proved that the early universe had the density fluctuations necessary to grow into cosmic structure. The map of these fluctuations became the baby picture of the universe, showing the seeds of everything that would later form. Subsequent missions refined this map with increasing precision. The Wilkinson Microwave Anisotropy Probe WMAP, launched in 2001, created detailed maps showing the CMB's temperature variations at much higher resolution. Then in 2009, the European Space Agency's Planck satellite achieved even greater precision, mapping the CMB with extraordinary detail and measuring not just temperature, but also polarization of the ancient light. The patterns in the CMB map aren't random, but contain crucial information about the universe's composition and geometry. The size and amplitude of the temperature variations depend on the density of ordinary matter, and dark energy. The geometry of the patterns reveals the curvature of space itself. By analyzing the CMB with exquisite care, cosmologists can determine fundamental parameters. The universe is 13.8 billion years old, flat in its geometry, composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy. The hot and cold spots in the CMB represent regions that were slightly denser or less dense than average in the early universe. Denser regions appeared as hotspots because gravitational compression heated them. These same denser regions would later become the locations where galaxies and clusters formed. The CMB map is literally a blueprint for cosmic structure, showing where matter would eventually concentrate. One of the most remarkable features in the CMB is the acoustic peaks, oscillations in the temperature power spectrum that reveal how sound waves propagated through the early universe. Before recombination, pressure waves rippled through the hot plasma, creating periodic variations in density. These acoustic oscillations left their imprint on the CMB as a characteristic pattern of peaks at specific angular scales. The spacing of these peaks provides one of the most precise measurements of the universe's composition and geometry. The CMB also reveals the universe's large-scale geometry. If space had positive curvature like a sphere's surface, distant CMB features would appear larger than expected. If space had negative curvature like a saddle, features would appear smaller. Measurements show the CMB features have exactly the angular size predicted for flat space. The universe, at the largest scales we can observe, is geometrically flat, extending as far as we can see with no overall curvature. But the CMB isn't perfectly smooth. Besides the tiny primordial variations, the ancient light has been modified during its journey across billions of light years. Photons passing through galaxy clusters gain energy from the hot gas, creating tiny temperature increases called the Sunyaev-Zeldovich effect. These modifications actually help us map massive structures between us and the CMB, providing another tool for understanding the cosmic web. The CMB also shows us something else crucial. The universe began in an incredibly smooth state, with density variations of only 1 part in 100,000. The dramatic structures we see today, galaxies and clusters and voids, all grew from these tiny initial seeds through gravitational amplification over billions of years. Gravity took whisper-quiet fluctuations and amplified them into roaring concentrations of matter. The journey from the smooth CMB to the lumpy present-day universe is the story of structure formation. Some anomalies in the CMB remain puzzling. There's a mysterious cold spot, larger than expected from random fluctuations that might be associated with a supervoid along our line of sight. The largest scale patterns show hints of asymmetry, with one hemisphere slightly warmer than the other. Whether these features represent deep physics or statistical flukes remains debated but they remind us that even our most precise maps contain mysteries. Modern analyses of the CMB combine it with maps of galaxies and clusters from surveys across cosmic time. By comparing the universe's initial conditions, shown in the CMB, with its evolved state today, cosmologists test their models of structure formation. The fact that simulations starting from CMB-measured initial conditions produce structures matching what we observe is one of the great triumphs of modern cosmology. As you contemplate the CMB tonight, recognize it as the oldest map we possess, a photograph of the universe when it was just 380,000 years old, less than 100,000th its current age. Every structure we've discussed, from solar systems to superclusters, originated from the tiny variations visible in this ancient light. The map of the cosmic microwave background is the foundation upon which all our other cosmic maps rest, the initial conditions from which everything else grew. We've mapped the universe's structure across vast scales, from our solar system to Laniakea and beyond. But maps raise questions about origins. How did these structures form? How did the nearly smooth universe, revealed by the cosmic microwave background, transform into the complex cosmic web we observe today? The answer lies in understanding the physics of structure formation, the patient work of gravity, amplifying tiny initial fluctuations into magnificent architecture. The story begins with quantum mechanics in the first fraction of a second after the Big Bang. During cosmic inflation, quantum fluctuations in the fabric of space-time itself were stretched to cosmic scales. These fluctuations became variations in density, regions where the universe was ever so slightly more or less dense than average. The variations were tiny, about 1 part in 100,000, but they were there, imprinted across all scales, from small to vast. As the universe expanded and cooled, these density fluctuations began to evolve under gravity. Regions that were slightly denser had slightly stronger gravitational fields, pulling in more matter from their surroundings. This made them denser still, strengthening their gravity, attracting even more matter. Gravity is a runaway process, an instability where small differences grow exponentially larger over time. Dense regions get denser, while underdense regions lose matter and become emptier. But this process didn't occur uniformly for all types of matter. In the early universe, ordinary matter, consisting of protons, electrons, and photons, was too hot and too strongly coupled to radiation for gravity to compress it. Radiation pressure resisted gravitational collapse. If the universe contained only ordinary matter, structures might never have formed or would have formed far too late to match observations. This is where dark matter becomes crucial. Dark matter doesn't interact with radiation, so it experiences no pressure resisting gravitational collapse. Even while ordinary matter remained smooth and hot, dark matter could begin clumping under gravity. Dark matter halos formed first, creating gravitational potential wells that ordinary matter could later fall into once the universe cooled enough. Dark matter provided the scaffolding, the gravitational architecture upon which visible structure would eventually build. Computer simulations have revealed this process in stunning detail, starting with initial conditions matching the fluctuations observed in the cosmic microwave background. Astronomers evolved billions of dark matter particles forward in time under gravity and cosmic expansion. What emerges is the cosmic web we observe: filaments, connecting clusters, sheets surrounding voids, a foam-like structure at the largest scales. The simulations show how structure formation proceeds hierarchically. Small structures form first, then merge and accrete to form progressively larger structures. This bottom-up formation creates a self-similar pattern, where structure appears at every scale examined. The same gravitational physics that forms galaxies forms clusters, just operating across different timescales and spatial scales. For ordinary matter, the process is more complex. Once the universe cooled enough for ordinary matter to decouple from radiation, it began falling into the dark matter potential wells. But ordinary matter can radiate energy by emitting light and other radiation. This cooling allows it to condense more efficiently than dark matter, concentrating into dense cores at the centers of dark matter halos. These dense concentrations become the sites where stars and galaxies form. The first stars probably formed around 100 million years after the Big Bang, in small dark matter halos containing enough ordinary matter to cool and collapse. These primordial stars, made only of hydrogen and helium, with no heavier elements, were likely massive and short-lived. When they exploded as supernovae, they enriched space with the first heavy elements and may have provided the seeds for supermassive black holes. Galaxies formed through a combination of smooth accretion of gas and mergers of smaller systems. Most large galaxies, like the Milky Way, assembled through countless mergers of smaller galaxies over billions of years. The archaeological evidence remains visible in stellar streams, disrupted satellite galaxies stretched into tidal tails, and the old stellar populations in galactic halos that represent the first systems to merge. Galaxy clusters formed later as rare peaks in the initial density field where multiple filaments intersected. These regions had enough mass to collapse into gravitationally bound systems despite the universe's expansion. The most massive clusters are still forming today through mergers of smaller clusters, violent collisions that heat the intra-cluster gas and send shockwaves rippling through space. The cosmic web's filamentary pattern emerged naturally from the geometry of gravitational collapse. The initial density fluctuations weren't spherical, but had complex shapes. Gravitational collapse proceeds fastest along the shortest dimension, creating sheets first. Sheets then collapse along their shorter dimension, creating filaments. Finally, filaments fragment and collapse into dense nodes, where clusters form. This geometric progression from smooth to sheet to filament to cluster creates the web we observe. One of structure formation's most striking features is its self-limiting nature. In the densest regions that became galaxy clusters, matter accumulated so rapidly and from such high velocities that collisions heated gas to millions of degrees. This hot gas radiates X-rays, losing energy, but can't cool efficiently at these temperatures. The hot gas creates pressure that resists further collapse, halting star formation in cluster cores. This is why cluster galaxies are red and dead, while field galaxies continue forming stars. Cosmic expansion also plays a crucial role. The expansion of space works against gravity, making it harder for structures to collapse. Only regions dense enough to overcome expansion can collapse into bound structures. As dark energy accelerates cosmic expansion in recent cosmic epochs, structure formation slows. Clusters forming today will be the last major structures to collapse. Eventually, expansion will prevent any new structure formation. Modern structure formation models match observations remarkably well. Simulations reproduce not just the cosmic web's appearance, but quantitative details: the abundance of galaxies of different masses, the properties of galaxy clusters, the distribution of voids. The success of these models, starting from initial conditions measured by CMB observations and using known physics, provides powerful confirmation of our cosmological understanding. Yet mysteries remain. Simulations predict more small galaxies than we observe. The missing satellites problem we discussed earlier. Predicted dark matter halos have denser cores than observations suggest. These discrepancies might indicate missing physics in our understanding of how galaxies form within dark matter halos, or possibly that dark matter's properties differ from our assumptions. As you reflect on structure formation tonight, consider the grandeur of this process. Quantum fluctuations from the universe's first instant, amplified by gravity across billions of years, created everything from galaxies to superclusters. The universe began nearly smooth and evolved into magnificent complexity through the patient work of gravity. The structures we map today are gravity's sculptures, carved from primordial density variations over cosmic time. As we've journeyed outward from our solar system through ever larger structures, we must eventually confront a fundamental limit. There's an edge to what we can observe, not because the universe ends there, but because light from more distant regions hasn't had time to reach us since the universe began. Understanding this cosmic horizon reveals profound truths about the nature of space, time, and the limits of cosmic cartography. The observable universe is defined by a simple principle. We can only see light that has had time to reach us since the Big Bang 13.8 billion years ago. You might expect this means the observable universe extends 13.8 billion light-years in every direction, creating a sphere 27.6 billion light-years across. But the reality's far more interesting because space itself has been expanding while that light travelled toward us. When we observe a galaxy whose light has been travelling for 13 billion years, we're seeing it as it appeared 13 billion years ago when it was much closer to us. But during those 13 billion years of light travel, space has been expanding, carrying that galaxy farther away. The galaxy we see in the distant past is now much farther than 13 billion light-years away. Accounting for this expansion reveals that the observable universe extends about 46.5 billion light-years in every direction, creating a sphere 93 billion light-years across. This presents a beautiful paradox. We're surrounded by a sphere 93 billion light-years across, yet the universe is only 13.8 billion years old. The resolution lies in understanding that space itself expands. Distances between galaxies increase, not because galaxies move through space, but because new space continuously appears between them. The cosmic horizon marks not where the universe ends, but where light hasn't had enough time to reach us, given the universe's expansion history. The most distant light we can observe is the cosmic microwave background itself, emitted when the universe was 380,000 years old. This radiation comes from a spherical shell surrounding us, called the surface of last scattering, where atoms first formed and photons began travelling freely. This surface now lies about 46 billion light-years away due to expansion. We cannot see beyond this surface with light because the earlier universe was opaque plasma. But the cosmic horizon is receding. As time passes, light from more distant regions reaches us, slowly expanding what we can observe. Each second, the observable universe grows larger as new regions come into view. However, this growth is not what you might expect, because cosmic expansion is accelerating due to dark energy. Distant regions are receding faster than nearby ones. Eventually, galaxies will cross a threshold where space between us expands faster than light can travel through it. This creates two different horizons. The cosmic horizon marks the most distant regions whose light can have reached us. The event horizon, distinct from the cosmic horizon, marks the most distant regions whose light will ever reach us, given accelerating expansion. Galaxies beyond the event horizon are receding so fast that their light, despite travelling toward us, will never arrive because space expands faster than light travels. These galaxies are permanently beyond observation. Current measurements suggest the event horizon lies at a co-moving distance of about 16 billion light-years. Galaxies beyond this distance, though their light may currently be reaching us, will eventually recede beyond observation as expansion accelerates. In the far future, distant galaxies will fade from view as they cross this horizon, disappearing from the observable universe forever. Our maps will encompass a shrinking fraction of the total cosmos. The nature of these horizons reveals something profound about cosmic structure. All the structures we've mapped, from galaxy clusters to superclusters to the cosmic web itself, exist within our observable universe. But the universe almost certainly extends beyond what we can see. beyond our cosmic horizon, space likely continues with more galaxies, more clusters, more structure, stretching far beyond what we'll ever observe. What does beyond mean in this context? It doesn't mean beyond an edge in space, but beyond a limit in time. The universe beyond our horizon isn't separated from us by a wall, but by insufficient time for light to have travelled. These regions exist right now, in the present moment according to cosmic time, but we cannot observe them because their light hasn't reached us yet and, in many cases, never will. The shape of our observable universe depends on cosmic geometry. If space has positive curvature, like a sphere's surface, the observable universe would curve back on itself and be finite in size. If space has negative curvature, like a saddle, the universe would be infinite, with the observable portion being an infinite, flat plane. Measurements of the cosmic microwave background reveal space is flat to high precision, suggesting the universe is either exactly flat and infinite, or so large that its curvature is undetectable even across observable scales. This flatness has implications for the total size of the universe. If space is precisely flat, the universe is infinite, extending forever beyond our horizon. The observable universe would then be an infinitesimal fraction of the total, a small bubble in an infinite ocean of space containing infinite galaxies and infinite structure. If space has slight curvature, the universe could be finite, but still vastly larger than what we observe, perhaps hundreds or thousands of times larger. Astronomers map the observable universe by conducting redshift surveys, measuring distances to millions of galaxies and plotting their three-dimensional positions. The most distant galaxies we observe appear highly redshifted, their light stretched by cosmic expansion until visible light becomes infrared. The James Webb Space Telescope and other instruments push this frontier, discovering galaxies at higher and higher redshifts, filling in our map of the early universe. But we must always remember that our maps are incomplete. They show only the observable portion of a potentially infinite cosmos. Every map of the universe is provisional, limited by cosmic horizons we cannot cross. We're mapping an island in an ocean, surrounded by regions we can never observe, charting what we can see while knowing vast structure lies forever beyond our reach. As you contemplate the edge of observation tonight, recognize both the achievement and the limitation. We've mapped the observable universe across 93 billion light-years, charting structure from our solar system to the cosmic horizon. Yet we know this represents only what we can see, a fraction of what exists. The universe almost certainly extends beyond our horizon, containing wonders we'll never map. This is the ultimate humility of cosmic cartography, recognizing that the complete map can never be drawn. Our map of the universe would be incomplete without understanding the force that's currently reshaping cosmic structure, pulling apart the largest assemblies we've described, and determining the ultimate fate of everything we can observe. Dark energy, the mysterious component that makes up about 68% of the universe's total energy, is accelerating cosmic expansion and slowly isolating structures from one another. Understanding dark energy is crucial to mapping not just where things are, but where they're going. The discovery of cosmic acceleration in 1998 was completely unexpected. Two teams of astronomers studying distant supernovae, stellar explosions that serve as cosmic distance markers, found that these ancient explosions appeared dimmer than expected. The only explanation that fit the data was that the universe's expansion is accelerating. Space is expanding faster now than it was billions of years ago. Something is pushing the universe apart, working against gravity's tendency to slow expansion. This accelerating force was dubbed dark energy, and its discovery revolutionized cosmology. For the first time, astronomers had evidence of a component of the universe that creates repulsive gravity, a pressure that pushes space apart rather than pulling things together. The discovery earned the 2011 Nobel Prize in Physics and forced a fundamental revision of our cosmological models. The simplest explanation for dark energy is Einstein's cosmological constant, a term Einstein originally added to his equations to create a static universe, then called his greatest blunder after Hubble discovered cosmic expansion. Ironically, observations now suggest Einstein's constant was prescient. A cosmological constant represents an energy density inherent to space itself. As space expands, new space appears, bringing new dark energy with it. This creates an accelerating expansion that grows stronger as the universe ages. But we don't know what dark energy actually is. A cosmological constant would have to be incredibly fine-tuned, with a value orders of magnitude smaller than quantum physics suggests it should be. Alternative theories propose dynamical dark energy, fields that vary over space and time rather than remaining constant. Some models suggest modifications to gravity itself at cosmic scales. Despite intensive theoretical and observational efforts, dark energy remains profoundly mysterious. The effects of dark energy on cosmic structure are dramatic and increasing. At early times when the universe was small and dense, gravity dominated and structure grew as matter clumped under gravitational attraction. But as the universe expanded and dark energy's influence grew, structure formation began to slow. About 5 billion years ago, dark energy became dominant, and structure formation essentially halted at the largest scales. Galaxy clusters, the largest gravitationally bound structures, are the last major objects to form. Clusters still growing today through mergers represent the final chapter of structure formation. As dark energy accelerates expansion, it becomes increasingly difficult for matter to overcome expansion and collapse into new clusters. Eventually, no new clusters will form. The map of galaxy clusters we see today represents nearly the final census of these structures. On larger scales, the effects are even more dramatic. Superclusters like Laniakea are not gravitationally bound. Dark energy is pulling them apart, slowly increasing the distances between member clusters. The gravitational flows we observe within Laniakea are being weakened by accelerating expansion. Eventually, these flows will reverse as expansion overcomes gravity, and the supercluster will dissolve into isolated clusters receding from one another. The local group, being gravitationally bound, will resist dark energy's influence. The Milky Way and Andromeda will still merge as planned, and the resulting merged galaxy will remain intact, but structures beyond the local group will recede from view. Eventually, billions of years in the future, expansion will have carried distant galaxies beyond our cosmic horizon. An observer in the far future will see only the merged local group surrounded by darkness with no other galaxies visible. This creates a disturbing possibility for future cosmic cartographers. In the far future, all evidence of the larger universe will have disappeared from view. The cosmic microwave background will have redshifted to undetectably long wavelengths. All galaxies outside the local group will have receded beyond observation. A future astronomer would observe only their local galaxy surrounded by empty space and might reasonably conclude the universe contains nothing else. All our carefully constructed maps of cosmic structure would be impossible to recreate. Dark energy also affects how we interpret observations. When we measure the distances and velocities of galaxies to create three-dimensional maps, we must account for dark energy's acceleration. The redshift distance relationship differs from what it would be in a non-accelerating universe. Careful modeling of dark energy's effects is crucial for accurate cosmic mapping. Current observations constrain dark energy's properties but don't reveal its nature. Measurements suggest dark energy behaves very much like a cosmological constant, remaining constant in density as space expands. But the precision of current data leaves room for slight evolution in dark energy's strength over cosmic time. Next-generation surveys mapping millions of galaxies and measuring their distances precisely will test whether dark energy truly is constant or whether it varies. Some cosmologists speculate that dark energy might not be a fundamental field, but an illusion arising from averaging the universe's clumpy structure. In this view, our observations might be biased by our particular location within cosmic structure, creating an apparent acceleration. However, most evidence suggests dark energy is real, a genuine component of the universe's energy budget. The ultimate fate of structures depends entirely on dark energy's nature. If dark energy is a true cosmological constant, expansion will accelerate forever. Galaxies will recede, structures will dissolve, and eventually even-bound structures like galaxies might be torn apart in a big rip if acceleration becomes extreme enough. If dark energy weakens over time, gravity might eventually regain dominance, potentially even reversing expansion into a big crunch. Understanding dark energy is crucial for extending our cosmic maps forward in time. We can map where structures are now with increasing precision. Dark energy determines where they'll be billions of years hence. It shapes the future geography of the cosmos, determining which structures will persist and which will dissolve into isolation. As you reflect on dark energy tonight, recognize it as the force reshaping the very structures we've mapped. The cosmic web, assembled over billions of years by gravity, is now being slowly dismantled by accelerating expansion. Dark energy is writing the final chapter of cosmic structure formation, determining the ultimate fate of everything from galaxy clusters to the observable universe itself. It's a force we don't understand, pulling apart a universe we're only beginning to map. As we push toward the boundaries of the observable universe, some of the most careful thinking in modern physics suggests our map might be radically incomplete in a way we haven't yet discussed. The structures we've charted, from solar systems to superclusters spanning billions of light years, might represent only one universe among countless others. The multiverse hypothesis proposes that reality extends far beyond what we can observe, encompassing many universes with different properties, different laws of physics, perhaps even different dimensions. The idea of a multiverse arises from several independent lines of theoretical reasoning, each suggesting that our universe might not be unique. These different types of multiverse aren't mutually exclusive, but represent different levels or categories of cosmic structure beyond what we've mapped. The simplest multiverse is level 1, an infinite universe extending beyond our cosmic horizon. If space is infinite and uniformly filled with matter at cosmic scales, then everything that can happen will happen infinitely, many times in different regions. There would be infinite copies of our observable universe, infinite Earths, infinite versions of you reading these words. These parallel regions would be forever beyond observation, separated by distance and cosmic expansion, but they would be as real as the space around us. This isn't wild speculation, but a straightforward consequence of cosmic inflation and spatial flatness. If space is infinite and matter is distributed with the same statistical properties everywhere, the combinatorics are inevitable. With infinite volume, every possible arrangement of matter will occur infinitely often. The structures we've mapped would repeat in endless variations in regions far beyond our horizon. Level 2 multiverse arises from eternal inflation, a modification of the inflation theory that explains the universe's early rapid expansion. In eternal inflation, the inflating region doesn't stop everywhere simultaneously, but stops in random bubbles while continuing to inflate between them. Each bubble becomes a universe like ours, but different bubbles might have different values for fundamental constants, different particle physics, different effective laws of nature. This creates a vast landscape of bubble universes, each with its own properties, separated by exponentially expanding regions of inflating space. The bubbles can never interact or communicate, because the space between them expands faster than light can travel. Each bubble would have its own structure, its own galaxies and stars, potentially its own forms of life, adapted to whatever physics governs that particular universe. Level 3 multiverse comes from quantum mechanics, specifically the many worlds interpretation. In this view, every quantum measurement causes the universe to split into multiple branches, each corresponding to a different outcome. Every time a quantum event could go multiple ways, it does, in different branches of reality. These branches are real, existing in a vast multi-dimensional space called Hilbert space, though they cannot interact or communicate. If many worlds is correct, the universe continuously branches into astronomical numbers of parallel realities. Every choice you make, every quantum event in every atom, creates new branches. The map we've drawn represents just one branch among uncountably many, all equally real, all evolving according to the same quantum laws, but manifesting different outcomes. Level 4 multiverse is the most speculative, suggesting that all mathematical structures exist as physical realities. In this view, our universe corresponds to one particular set of mathematical laws, but other mathematical structures represent other universes with radically different properties. Some might have more or fewer dimensions, different fundamental forces, entirely alien physics. If a mathematical structure is logically consistent, it exists as a physical universe somewhere in this ultimate ensemble. The multiverse hypothesis raises profound questions for cosmic cartography. If other universes exist, can they be mapped? Are they part of the same space we inhabit, or separated by dimensions we cannot access? Does existence mean the same thing for regions beyond our cosmic horizon, and for bubble universes separated by inflating space? Some aspects of the multiverse might be testable. If our bubble universe collided with another during inflation, the collision might have left an imprint in the cosmic microwave background, a circular pattern of temperature variations. Astronomers have searched for such signatures without finding convincing evidence, though the searches continue. The absence of evidence doesn't mean other bubble universes don't exist, only that we haven't detected their influence. Critics argue that the multiverse isn't science because it makes no testable predictions. If we can never observe other universes, they say, the multiverse is philosophy or metaphysics, not physics. Proponents counter that the multiverse arises naturally from well-tested theories like inflation and quantum mechanics. If these theories are correct, the multiverse follows as a consequence, regardless of whether we can observe it directly. The multiverse also offers potential explanations for otherwise mysterious features of our universe. Why does our universe have the particular values for fundamental constants, like the strength of gravity or the mass of the electron? In a multiverse where different regions have different values, we observe the particular combination that allows life, because we can only exist in regions where those values permit stars, planets, and complex chemistry. This anthropic explanation is unsatisfying to some, but might reflect deep truth. From a mapping perspective, the multiverse represents the ultimate frontier. We've progressed from mapping our solar system to our galaxy, to the cosmic web, to the observable universe. The multiverse would be the final level, a map of all possible structures across all possible universes, but such a map might be fundamentally impossible. If other universes are truly beyond observation, they're beyond mapping. Yet there's something intellectually compelling about the multiverse, something that feels right about the idea that our observable universe isn't all that exists. Throughout history, humans have repeatedly discovered that our place in the cosmos is less special than we thought. We're not at the center of the solar system, or the galaxy, or the universe. Perhaps we're also not in the only universe, but in one region of a vastly larger multiverse. The mathematical structures describing the multiverse are fascinating in themselves. The landscape of possible universes in eternal inflation might contain 10 to the power of 500 distinct vacuum states, each representing a different possible universe. The branching structure of many worlds creates an ever-growing tree of realities. The space of all mathematical structures is infinite and infinitely complex. If the multiverse exists, it changes the meaning of our cosmic maps. They represent not the complete structure of reality, but one small corner of an unimaginably larger whole. Everything we've mapped, from our solar system to Laniakea to the cosmic horizon, would be a tiny patch in one bubble universe among countless others, itself embedded in an eternal, inflating space that might be infinite. As you contemplate the multiverse tonight, recognize both its speculative nature and its theoretical motivation. We don't know if other universes exist, but several independent lines of reasoning suggest they might, and some of the most careful thinkers in physics take the idea seriously. Whether the multiverse is real or not, considering it expands our conception of possible structure, pushing our maps to their ultimate limit. The structures we've mapped with such care might be embedded in something vastly larger, a multiverse of infinite variety and complexity. Or our universe might be all there is, unique and alone. Either way, the achievement of mapping what we can observe remains magnificent. We're creating the most complete picture possible of the cosmos we inhabit, while recognizing that the complete map might forever exceed our grasp. We've reached the boundary of what can be mapped through observation, but the human impulse to understand doesn't stop at horizons we cannot cross. What lies beyond the edge of the observable universe? If we cannot see it, observe it, or measure it, can we say anything meaningful about it? These questions push cosmology to its philosophical limits, while revealing deep insights about the nature of cosmic structure. The most conservative answer is that beyond our cosmic horizon, space continues much as it does within our observable region. This assumption, called the cosmological principle, holds that the universe is homogeneous and isotropic at large scales. It looks roughly the same everywhere, with no special locations or preferred directions. If the cosmological principle holds, the unobservable universe contains more galaxies, more clusters, more cosmic web, extending far beyond what we can see. Evidence supporting the cosmological principle comes from observations within our horizon. When we examine the universe at the largest scales we can observe, we find it looks statistically similar in all directions. Galaxy distributions, structure patterns, and the cosmic microwave background all show the same properties regardless of which direction we look. This suggests the universe doesn't have edges or centers, at least within observable regions. If space is infinite, as measurements of cosmic flatness suggest, then the universe beyond our horizon is literally infinite, containing infinite galaxies and infinite structure. Every possible arrangement of matter that can occur will occur infinitely many times. The cosmic structures we've carefully mapped would repeat in endless variations across infinite space, separated by distances so vast that light from those regions will never reach us. But infinity creates strange implications. In an infinite universe, somewhere beyond our horizon, there exists another region identical to our observable universe. The same galaxies, the same stars, the same Earth, with the same history. In fact, there would be infinitely many such regions, perfect copies of everything we know, embedded in an infinite sea of variations. These doppelganger regions would be real, governed by the same physics, yet forever beyond our ability to observe or influence. This raises questions about the nature of existence and reality. If something exists but can never be observed, even in principle, in what sense does it exist? Most physicists answer pragmatically. Mathematical and physical laws don't stop at observational horizons. If our equations predict structure beyond what we can observe, we should take those predictions seriously, even if we can't verify them directly. The horizon itself is receding, though not indefinitely. As we discussed, Accelerating expansion means that an event horizon exists beyond which regions will never become observable, no matter how long we wait. But before expansion accelerated about 5 billion years ago, the cosmic horizon was receding faster than it is now. Early observers would have been able to see regions that we can see today. In this sense, our observable universe is shrinking relative to what was once observable. This creates a poignant aspect of cosmic mapping. Every second, galaxies that are currently just beyond our horizon come into view as their light finally reaches us. But simultaneously, galaxies that we can currently observe are being carried beyond our event horizon by accelerating expansion. We're in a race between new regions becoming observable and current regions disappearing from view, and expansion is slowly winning. What about structure beyond what the cosmological principle predicts? Could the universe be different in unobservable regions? Some inflationary models suggest that while the universe might be homogeneous within each inflating bubble, different bubbles could have different properties. Our observable universe would lie entirely within one bubble, so we'd see homogeneity. But beyond our bubble's boundaries, radically different physics might operate. There's also the possibility that the universe is finite, but larger than our observable region. If space has slight positive curvature, the universe could wrap back on itself like the surface of a sphere, creating a closed cosmos, finite in volume, but without edges. In such a universe, traveling far enough in one direction would eventually return you to your starting point. The total volume would be larger than our observable portion, but not infinite. In a closed universe, we might even observe the same structure from multiple directions if light has had time to travel multiple times around the cosmos. Astronomers have searched for such repeated patterns in the cosmic microwave background without finding them, placing lower limits on the universe's size if it's closed. The universe must be at least hundreds of times larger than our observable region if it's finite. Another possibility is that the universe has a fractal structure extending beyond observation. Fractals show patterns that repeat at different scales, self-similar organization from smallest to largest. Some cosmologists have proposed that while the universe appears homogeneous at observable scales, it might show continued structure at larger scales we cannot see. However, measurements of the cosmic microwave background suggest the universe does become smooth at sufficiently large scales. The multiverse scenarios we discussed add another layer. Beyond our cosmic horizon might lie not just more of our universe, but other bubble universes with different physical laws, separated by eternally inflating space. These regions wouldn't just be unobservable, but might operate under fundamentally different physics, making even the concept of mapping them questionable. From a philosophical perspective, the existence of unobservable regions challenges our definition of knowledge. Science traditionally requires testability, the ability to verify predictions through observation. But if our best theories predict structure beyond observational access, we face a choice: accept these predictions as knowledge even without direct verification, or restrict knowledge only to what can be observed, rejecting theoretical extensions beyond horizons. Most cosmologists take the first approach. If a theory successfully predicts everything we can observe and is based on well-tested fundamental physics, its predictions about unobservable regions should be taken seriously. The same equations that describe structure within our horizon don't suddenly stop being valid at the horizon's edge. Mathematics and physics continue even where observation cannot. This has implications for the meaning of our maps. The cosmic structures we've charted represent a sample, a local region within a potentially infinite whole. Our maps are accurate for what they show, but necessarily incomplete. They're like maps of a small island, created by inhabitants who cannot leave the island or see beyond its shores. The maps are useful, even necessary, but the map makers know vast oceans lie beyond their reach. Yet there's beauty in this limitation. The fact that we can map anything at all, given our tiny vantage point in space and time, is remarkable. We're embedded in cosmic structure, one small system among countless others, yet we've managed to infer the shape of things billions of light years away. We've traced the history of structure formation back nearly to the beginning. We've understood, at least partially, the forces shaping cosmic evolution. As you contemplate what lies beyond observation, embrace both the knowledge and the mystery. We know the universe extends beyond our horizon, continuing with more structure, more galaxies, more cosmic web. We don't know if it's infinite or finite, whether it continues uniformly or changes dramatically beyond our view. These questions might never be answered completely, but asking them and understanding why we cannot answer them definitively represents its own form of wisdom. The ultimate map of the universe might be impossible to draw, but the attempt to create it has revealed wonders beyond imagination. We've mapped our cosmic neighborhood in exquisite detail and glimpsed structures at the very edge of observation. The unknown beyond doesn't diminish these achievements, but frames them, reminding us that every map shows only part of a larger territory that might extend forever. We've completed our journey from the solar system to the cosmic horizon and beyond, mapping every known structure the universe reveals. But before we rest, we should reflect on what this map-making means, what it reveals about us as much as about the cosmos. We are the universe mapping itself, consciousness that emerged from star stuff, now creating charts of the very structures that gave rise to consciousness. This recursive wonder deserves contemplation. Our ancestors mapped their immediate surroundings, valleys and rivers, hunting grounds and sacred places. They mapped what they could walk, what they could see from hilltops, what they could reach within a lifetime of travel. These maps were survival tools, encoding knowledge of where to find food and water, where dangers lurked, where home could be found. But humans have always wondered about what lies beyond the next valley. We are, at our core, explorers and mapmakers. We pushed beyond familiar territories, charting coastlines and continents. We mapped the Earth's surface until no unknown regions remained. Then we looked up. The celestial maps came next. Ancient astronomers catalogued stars and constellations, tracking planets across the sky, predicting eclipses and seasons. These maps served practical purposes, helping navigation and agriculture, but they also fed something deeper, the desire to understand our place in the cosmos. Even when the sky seemed an unchanging dome above a flat Earth, we were mapping it, imposing order on the apparent chaos of lights above. The Copernican revolution expanded our maps dramatically. Suddenly, Earth wasn't the center, but one planet among several orbiting the Sun. Our cosmic neighborhood grew from a small sphere to a solar system. Each subsequent expansion of our understanding brought new maps. Herschel mapping the Milky Way's structure, Curtis and Shapley debating whether spiral nebulae were island universes, Hubble proving they were, and discovering the universe expands. In the 20th century, cosmic cartography became quantitative and systematic. Large telescopes and photographic plates allowed astronomers to measure distances to thousands of galaxies. Radio telescopes revealed structure invisible to optical light. Satellites above Earth's atmosphere mapped the X-ray sky and the cosmic microwave background. Digital detectors and computers enabled surveys of millions of galaxies, creating three-dimensional maps of cosmic structure. Today's maps would astound our ancestors. We've charted our solar system with spacecraft, mapped our stellar neighborhood in 3 dimensions, understood our galaxy's spiral structure, despite being embedded within it. We've identified our local group of galaxies, mapped the Virgo cluster, discovered Laniakea. We've revealed the cosmic web extending across billions of light years. We've measured the universe's composition, age, and geometry. We've traced structure formation from the cosmic microwave background to the present day. These achievements represent collaborative efforts spanning generations. Thousands of astronomers building telescopes, conducting surveys, analyzing data, developing theory. Engineers creating the instruments that make observations possible. Computer scientists developing the algorithms to process vast data sets. Theorists creating models to explain what we observe. The maps we've discussed tonight are humanity's collective work, our species' attempt to understand where and what we are. The tools of modern cosmic cartography are extraordinary. The Sloan Digital Sky Survey has measured distances to millions of galaxies. The Gaia satellite has mapped the positions and motions of over 1 billion stars in our galaxy. The Planck satellite has measured the cosmic microwave background with exquisite precision. The James Webb Space Telescope is discovering galaxies near the cosmic horizon. Each instrument adds detail to our maps, filling gaps, refining boundaries, revealing new structures. But perhaps most remarkable is that we can make these maps at all. We're confined to one small planet, orbiting one typical star in one galaxy among billions. We cannot leave our solar system, cannot visit other galaxies, cannot view the universe from outside. Yet from this limited vantage point, we've inferred structure across billions of light years. We've understood the physics governing cosmic evolution. We've created maps that, while incomplete, capture genuine truths about reality's largest structures. This is possible because the universe is comprehensible. The same physical laws that operate on Earth govern the cosmos. Light carries information across space, encoding details about its source. Mathematical patterns reveal themselves in observations. Nature is consistent, allowing us to generalize from what we observe locally to conditions across vast distances. If the universe were chaotic or governed by laws that changed arbitrarily, cosmic cartography would be impossible. Our maps also reveal how much we don't know. Dark matter dominates cosmic structure, yet we don't know what it is. Dark energy accelerates expansion, but its nature remains mysterious. We've mapped only the observable universe, which might be a tiny fraction of the total cosmos. The multiverse hypothesis suggests realities beyond our mapping capability. Every question we answer reveals new questions, deeper still. Yet this ignorance doesn't diminish the achievement. The Socratic wisdom, "I know that I know nothing," represents profound understanding. Recognizing the limits of our knowledge, understanding what we cannot yet map, is itself a form of mapping. We're charting not just structure, but the boundaries between knowledge and mystery, observation and speculation, the mappable and the unmappable. There's something poetic about consciousness arising in the universe and turning its attention outward to map the cosmos. We are, as Carl Sagan said, a way for the universe to know itself. The atoms in our bodies were forged in stars, scattered by supernovae, gathered by gravity into planets. The structures we've mapped created us. Now we create maps of those structures, closing a loop of cosmic self-reflection. This might be rare in the cosmos. We don't know if other intelligences exist, if other mapmakers chart their regions of space. But whether we're alone or one among many, the achievement stands. Humanity has created comprehensive maps of cosmic structure from our small world. We've extended our understanding from solar systems to superclusters, from the observable universe to theoretical multiverses. These maps serve purposes beyond pure knowledge. They provide context for our existence, situating us in space and time. They reveal we're not central or special in location, but occupy a typical region of a typical galaxy in a typical part of the cosmic web. This cosmic humility is valuable, tempering any tendency toward cosmic arrogance. We're small, recent, confined to one small world in a vast universe. Yet we're also significant in being able to understand this. The universe produced structures that became self-aware and curious. We matter not because we're central, but because we're conscious participants in cosmic evolution, observers who can appreciate and map the magnificence around us. Our significance comes from understanding, from the maps we make, from the questions we ask. The future of cosmic cartography is bright. Next-generation telescopes will discover galaxies near the cosmic horizon. Gravitational wave detectors will map massive objects through ripples in space-time. Neutrino observatories will chart the universe through ghostly particles. Each new tool extends our maps, adds detail, reveals structure previously hidden. But we must also accept that some maps will remain incomplete. The universe beyond our horizon cannot be observed. The multiverse, if it exists, might forever exceed observational access. Dark matter might not reveal its nature, despite our best efforts. Some questions might not have answers we can discover. The complete map might be impossible. There's melancholy in this, but also acceptance. We're finite beings in a possibly infinite cosmos. Our lifespans are brief, our reach limited, our understanding partial. We cannot map everything or understand completely. But we can map what we can reach and understand what we can grasp. We can create the best maps possible given our limitations. These maps are gifts to future generations. Every survey catalogues objects and measures distances that later astronomers can study in new ways. Every observation adds to humanity's collective knowledge. The cosmic microwave background maps we create today will be analysed by scientists not yet born, possibly revealing insights we cannot currently imagine. Our maps also remind us that perspective matters. We map from our location in space and time, using tools and concepts available to us now. Future mapmakers with better instruments and deeper understanding might create maps that reveal our errors and omissions, but they'll build on our work, extending rather than discarding it. Scientific progress is cumulative. Each generation sees further by standing on the shoulders of giants. As you drift towards sleep tonight, reflect on this extraordinary fact. You've journeyed through a map of the universe created by your fellow humans, your cosmic family. Every structure we've discussed, from planets to superclusters, has been observed, measured, and understood through human effort. The map exists because we made it, because we wondered what lay beyond our world and looked up with both eyes and instruments to find out. You reside in a solar system, orbiting a star in a galaxy called the Milky Way, which belongs to the local group of galaxies, which falls within Laniakea supercluster, which is part of the cosmic web extending across the observable universe, which might be embedded in a multiverse of infinite complexity. This is your cosmic address, your place in the grandest structure we know, but you're also a map maker, even if you've never looked through a telescope. By wondering about the cosmos, by seeking to understand your place within it, you participate in the great project of cosmic cartography. Every person who looks up at the night sky and asks what's out there contributes to humanity's collective effort to map the universe. The night sky above you right now connects to everything we've discussed. Those points of light are mostly stars in our galaxy, typically dozens to hundreds of light years away. The Andromeda Galaxy, visible to the naked eye from dark locations, represents light that traveled 2.5 million years to reach you. Every photon entering your eye is a tiny map, carrying information about its source across vast space. Close your eyes now and imagine the nested structures we've mapped. Your planet orbiting its star, your solar system moving through the local bubble, your galaxy spinning in the local group, everything falling through Laniakea toward the great attractor, the cosmic web stretching in all directions. The observable universe surrounding you like an enormous sphere, and beyond perhaps an infinite cosmos or infinite multiverse, unmappable but real. We are cosmic cartographers, you and I and all of humanity. We map because we wonder, because we're curious, because understanding where we are helps us understand who we are. The universe is vast and mysterious, but it's knowable to the extent we can observe it. Each generation extends the maps a bit further, adds detail, refines understanding. As sleep approaches, let the boundaries between here and there soften. You're not separate from the structures we've mapped, but embedded within them, made of star stuff, formed by cosmic evolution, conscious nodes in the universe's vast network. The map we've created tonight is also a map of you, tracing your origins from the Big Bang through structure formation to this moment. Rest now in your cosmic context. You exist in a solar system, in a galaxy, in a supercluster, in an observable universe, possibly in a multiverse. The same atoms that form your body have journeyed across billions of years and light years through stars and supernovae, through cosmic evolution, arriving here and now as you. The map is incomplete and always will be, but it's beautiful, intricate, revealing magnificent structure across the largest scales we can observe. We've traced cosmic architecture from the smallest worlds to the grandest clusters, from the nearest stars to the most distant horizons. We've created maps that capture, however partially, the shape of reality itself. Thank you for joining this exploration here on Whispering Universes. Thank you for being fellow travelers, cosmic companions, map makers, charting the universe together. The structures we've mapped tonight will persist long after we're gone, evolving slowly under gravity and expansion, following paths we can now predict because we've learned to map them. As you dream, perhaps you'll wander through the structures we've discussed, drifting through the cosmic web, seeing the universe from perspectives we can only imagine. Perhaps in your dreams you'll stand outside the observable universe and see it whole, a sphere of structure embedded in larger mystery. Perhaps you'll glimpse the multiverse, infinite realities branching in infinite directions. Or perhaps you'll simply rest in the knowledge that you exist in a universe we can partially understand, can partially map, can partially comprehend. That itself is enough. We are the cosmos knowing itself, however imperfectly, however partially. Sleep well, dream deeply, rest peacefully in your place within the mapped universe. The structures wait patiently, continuing their slow evolution, their magnificent dance across billions of light years, whether we observe them or not. Welcome home to the cosmos. Welcome home